So the whole test is just doing different integrals. So there are 10 of them. And so if we look at number 1, we have the integral of x cosine of 5x dx. And it doesn't tell us how to integrate, but because we can see that we have two different functions, one of the ways that we know how to integrate two different functions is by integration by parts. So we're going to have to pick an f of x and a g prime of x. So if I let f of x equal x and g prime of x equal cosine of 5x, then f prime of x equals 1, g of x equals 1/5 sine of 5x. Okay, and our integration by parts formula is f of x times g of x minus the integral g of x f prime of x dx. So if we put our pieces together, f of x is x, g of x is 1/5 sine of 5x, and then g of x is 1/5 sine of 5x, f prime of x is 1, so you end up with x times 1/5 sine of 5x minus the integral 1/5 sine of 5x times 1 dx. And so in simplifying, I would get x over 5 sine of 5x for my first part, minus 1 times 1/5 is just 1/5, so I'm going to pull the 1/5 out front, and I would have the integral of sine of 5x dx. The integral of sine of 5x is 1/5 negative cosine of 5x, so I'd end up with 1 over 25. Negative cosine makes that a plus, so plus 1/25 cosine of 5x plus c, because the integral of sine of 5x is 1/5 is negative 1/5 cosine of 5x, and 1/5 times 1/5 gives me the 25, and negative times a negative gives me positive. So you end up with x over 5 sine of 5x plus 1/25 cosine of 5x plus c. Any other questions on number 1? Okay. If I look at number 2, I'm given the integral of the natural log of the cube root of x dx. So I'm going to do the same thing. I'm going to integrate by parts. So I'm going to let f of x equal the natural log of the cube root of x. G prime of x is going to equal my second function, which in this case would be if I just added a 1 into that function. So if I integrate 1, I get x. If I go through integrating the natural log of the cube root of x, it actually integrates to 1 over 3x, or derives to 1 over 3x, I believe. So f of x, g of x, minus the integral g of x, f prime of x dx. So f of x is the natural log of the cube root of x. G of x is just x. G of x is x. F prime of x is 1 over 3x dx. So in simplifying, this becomes x natural log of the cube root of x. Over here, these x's cancel. So end up with minus the integral of 1/3 dx. And the integral of 1/3 is just 1/3 x plus c. So I end up with x natural log of the cube root of x minus 1/3 x plus c. So any questions on number 2? Nope. All right, on number 3, we went over in section 7.5, I believe, that the easiest way to integrate definite integrals is using your calculator. So we're going to use our calculator on number 3 because it's a definite integral. So the first thing we have to do whenever we're using definite integrals and using our calculator is to graph our function. So on number 3, our function is x cubed natural log of x. Okay, so if you graph that function, you get this kind of almost like a half a parabola shaped graph. And then to find your integral, you go to your second calc button, and your 7th option down is the integral of f of x dx. In this case, our lower limit is 1, and our upper limit is 3. And so the area underneath our graph from 1 to 3 is approximately 17.247. So approximately 17.247 by calculator. Okay, so whenever you have definite integrals, meaning you have upper and lower limits that are numeric, then you can use your calculator. All right, if I look at number 4, I'm given the integral of sine squared of x cosine cubed of x dx. And we went over how to solve trigonometric integrals using our trig substitution. Okay, so I'm going to start with u and du substitution. So if I let u be sine of x, what's the derivative of sine of x? Positive cosine. So cosine of x. And then I also know that one of my trig identities is that cosine squared of x is equal to 1 minus sine squared of x. So I'm going to rewrite this integral. Sine is going to become u, so u squared. I'm going to save out 1 cosine of x, so I would have cosine squared times cosine of x. One of those cosines of x becomes du, and the other cosine squared function becomes 1 minus sine squared, but sine is u, so 1 minus u squared. In doing that, then I can distribute my u squared, so I get u squared minus u to the 4th du. And from there, I can just integrate straightforward. So what does u squared integrate to become? Yep, u cubed over 3. What does u to the 4th integrate to become? U to the 5th over 5 plus c. And then if I back substitute what u equaled, which is sine of x in there, I would get sine cubed over 3 minus sine to the 5th over 5 plus c. If I look at number 5, I'm given the integral from 0 to pi of sine squared of x cosine cubed of x dx. Because this is a definite integral, the easiest thing to do is to use our calculator. So we're going to graph sine squared of x cosine cubed of x into our graphing calculator. So sine of x squared cosine of x cubed So we end up with this very strange cosine and sine graph where it's like staying above and below our axis for 2 whole periods. Then if we want to make sure, since we're going from 0 to pi, we want to make sure we're in radian mode. So you check your calculator, make sure you're in radian mode. So my calculator is in fact in radian mode. So I'll go back to my graph and then go to second calc. Option 7 is your integration option. Our lower limit in this case is 0. Our upper limit in this case is pi. And so our area from 0 to pi is a very tiny area. So in this case, then we would put negative 7.71 times 10 to the negative 15, because E just stands for times 10 to the negative 15. So you put that instead of putting 15 or 14 zeros, because that would be a lot of zeros. You can just write it like that. All right, on number 6, we're given the integral from tangent of x to secant cubed of x dx. And again, with our trig substitution rules, I'm going to let u be secant of x. The derivative of secant is secant tangent. So I need to pull out a secant for my derivative. So I'm going to rewrite this as secant of x, secant squared of x. That's the same thing as secant cubed. I still have 3 secants. I just pulled one of them out. So then in rewriting my integral, that secant squared becomes u squared. The secant tangent becomes du. So I end up with u squared du. And what's the integral of u squared? U cubed over 3 plus c. So you end up with secant cubed of x over 3 plus c. If I look at number 7, I'm given the integral from negative infinity to 0 of secant to the 4th of x tangent squared of x dx. Because you can't evaluate negative infinity in your calculator, we can't use our calculator to solve this. So we're just going to have to rewrite this as the limit as t approaches. The limit as t approaches negative infinity of the integral from t to 0, secant to the 4th of x, tangent squared of x dx. Then I'm going to use my u substitution, but u be, well, in this case, because we are dealing with even exponents, I'm going to let u be tangent of x, which means du equals secant squared of x. And I know that secant squared of x equals 1 plus tangent squared of x. That's one of your trig identities. So I'm going to rewrite this as secant squared of x times secant squared of x, so that one of those secant squareds can be used as du. So this becomes the limit as t approaches negative infinity from t to 0 of 1 plus u squared times u squared du. Because that secant squared becomes 1 plus tangent squared, but tangent is u. The other secant squared becomes du, and the tangent squared becomes u squared. If I keep simplifying and distribute my u squared, I get the limit as t approaches negative infinity of the integral from t to 0 of u squared plus u to the 4th du. And what's the integral of u squared? U cubed over 3. And what's the integral of u to the 4th? U to the 5th over 5. So then in rewriting, I'm going to evaluate that from t to 0. So then in rewriting that, I get tangent cubed of x over 3 plus tangent to the 5th of x over 5. And I'm integrating that from negative infinity to 0. So then if I plug in my limits of integration, I get tangent cubed of 0 over 3 plus tangent to the 5th of 0 over 5 minus tangent cubed of negative infinity over 3 minus tangent to the 5th of negative infinity. Oh, that kind of looks like an 8. It's supposed to be an infinity symbol. Over 5. Okay, so let's simplify. What's tangent cubed of 0 over 3? What's tangent of 0? 0, and 0 cubed is 0, and 0 divided by 3 is 0. So tangent cubed is 0 over 3 is just 0. What is tangent to the 5th of 0 over 5? 0. Any idea what tangent does as it approaches negative infinity? It does get smaller. It does not exist because tangent is a graph that kind of goes like that as you look at it. And so as you're getting smaller, your graph starts over. So it does not exist for tangent cubed over 3. What do we think happens at tangent to the 5th of negative infinity over 5? The same. Yeah, it does not exist. Yep. Okay, so 0 plus 0 minus does not exist minus does not exist equals does not exist. Yep, if you get any does not exist in your equation, then you know that the limit does not exist. Okay, if I look at number 8, I'm given the integral from 0 to infinity of x divided by the square root of 36 minus x squared dx. So I'm going to rewrite this as the limit as t approaches infinity from 0 to t of that integral. So x over 36 minus x squared dx. I'm going to let x equal 6 sine of x. Dx equals 6 cosine of x then. And 36 minus x squared equals 6 squared cosine squared of x. Okay, so if I rewrite all of that, that x now becomes 6 sine of x. This 36 minus x squared becomes 6 squared cosine squared of x. And dx becomes 6 cosine of x. If I continue simplifying, this square root cancels with my squareds, so I end up with just 6 cosine of x on the denominator. And then that 6 cosine of x cancels with my dx, 6 cosine of x. So I end up with the integral from 0 to t of 6 sine of x. Okay, so what's the integral of 6 sine of x? Negative 6 cosine of x. Perfect. And I'm going to evaluate that from t to 0. So in doing that, I get negative 6 cosine of infinity minus negative 6 cosine of 0. Those minus and negatives becomes a positive. What is negative 6 cosine of infinity? Anybody know? As your cosine graph, which looks like this, gets closer and closer to infinity, what's happening to it? It just keeps going, right? It just keeps oscillating between 1 and negative 1. So the limit does not exist because your graph just keeps going up and down. It doesn't actually approach a number ever. And anyone know what 6 cosine of 0 is? 6, yep, because cosine of 0 is 1. 1 times 6 is 6. What does not exist plus 6 equal? Does not exist. Okay, so when your graphs aren't approaching a specific y value, then the limit does not exist. That happens more often than you think, especially with trig functions. Alright, and then 9 and 10 were our partial fraction problems. So if I look at number 9, I have x plus 15 divided by 5x squared minus 2x cubed. So the first thing I need to do is factor my denominator. What can I factor out of my denominator? X squared. So I'm going to put 5 minus 2x. So I can rewrite these fractions as a over x plus b over x squared plus c over 5 minus 2x. Okay, so if I need my denominator to be x squared times 5 minus 2x, to make this be an x squared, I'm going to multiply x by x and multiply by 5 minus 2x. To make this be x squared times 5 minus 2x, all I need to do is multiply by 5 minus 2x. And make this be x squared times 5 minus 2x, I need to multiply by an x squared. So in doing all of that, I get 5ax minus 2ax squared plus 5b minus 2bx plus cx squared. And you set that equal to your numerator, which is x plus 15. What would be my next step then? Group them. Yep. So I have a minus 2ax squared. And I have a cx squared, so minus 2a plus cx squared. I have a 5ax and a minus 2bx. And my only constant is just 5b. Okay, so once I've got my grouping done, what do I know that negative 2a plus c equals? How many x squareds do I have in my numerator? 0. So negative 2a plus c equals 0. How many plain x's do I have in my numerator? 1. So 5a minus 2b equals 1. And how many constants do I have in my numerator? What is 5b going to equal? 15. I have just a 15 as a constant. So let's start by solving the easy ones. If 5b equals 15, how do I solve that for b? Divide by 5. So what does b equal? Okay. If I then keep working backwards and try to solve 5a minus 2b equals 1, I get 5a minus 6 equals 1. Add 6. So a equals 7/5. And then if I keep going backwards, negative 2 times 7/5 plus c equals 0. Negative 2 times 7/5 is negative 14/5. What does c equal? 14/5. So then rewriting my fractions, I end up with 7 over 5x because a was 7/5. My b is just 3, so 3 over x squared. And my c is 14/5, so 14 over 5 times 5 minus 2x. Okay. Does that make sense? Sure. Alright, and so then the last one we did was 10, which was x squared minus 1 over x cubed plus x squared plus x. And our first step is always factor our denominator, so what can I factor out of my denominator? X, so I get x squared plus x plus 1, and that's all the further that will factor. So I can rewrite my partial fractions as a over x plus bx plus c over x squared plus x plus 1. So then in getting common denominators, I take a times x squared plus x plus 1 and bx plus c times x. And I end up with ax squared plus ax plus a plus bx squared plus cx equals x squared minus 1. So let's group some things together. Let's group our x squareds, our x's, and our constants. So I have an a x squared and a b x squared, so a plus b x squared. I have an a x and a cx, so a plus cx. And then my only constant left over is just a. So how many x squared terms do I have in my numerator? 1. How many x terms do I have in my numerator? 0. And what is my constant a equal to? -1. Okay, so a is already solved for us, so we can work backwards to solve the other two. So I plug in -1 into a plus c equals 0. I get -1 plus c equals 0. So what does c equal? 1. If I plug -1 plus b equals 1 in, then I get b equals 2. So in my equation, a over x, I get -1 over x plus bx, so 2x plus c, so plus 1 over x squared plus x plus 1. Okay, so any questions on this? Pretty straightforward. Okay, you guys will take your test tomorrow.